In this second part of the lesson, dedicated to the principal thermodynamic cycles, we see the Otto and the diesel cycle. Also, in this case, we refer to a real application and we make a simulation by using ideal and real gas models to see the differences among them. We start with the Otto cycle. This cycle is used to describe the most common combustion engines working with gasoline, with GPL or methane, and are typically represented in the diagram PV as displayed in the picture here below. The first transformation is adiabatic compression 1, 2. Then we have the isochoric heating 2, 3, the adiabatic expansion 3, 4, and the isochoric cooling 4, 1. We look for the heat and the work of every transformation to calculate the efficiency eta. In the first model, we adopt an ideal gas and isentropic transformations in place of the adiabatic ones, and the second model, a perfect gas and the adiabatic transformations are considered irreversible. And finally, we do a what-if analysis to understand what it changes with some parameter change. We remember that a perfect gas is a gas where the Cp and Cv, the heat capacities, are function of the temperature only. But still does exist the relationship that we have seen also for the ideal gases, Cv equals Cp minus R. Reason why we cannot use a real gas model for this application is a limit in the tool itself, the Thermonator tool, since the maximum temperature for real gases is limited to 1750 degrees, and here we need to stay higher. In reality, the cycle is including two more transformations, A and F. The transformation A is the isobaric filling the chamber from point 0 to point 1. Then we have the adiabatic compression, the isochoric heating, the adiabatic expansion, the isochoric cooling, and finally the isobaric emptying the chamber from 1 to 0. The steps are also represented graphically with the piston position inside of the cylinder and the corresponding opening of the valves. We remember that one cycle corresponds to 2 revolutions of the shaft. In the ideal case, the transformations 0, 1 and 1, 0 are opposite and there is no effect in the cycle. We consider here a real motor, the Nissan KA24DE60. The displacement is 2389 cubic centimeter, let's say 2.4 liters. The number of cylinders is 4. The power output 114 kilowatt at 5400 revolution per minute. The specific consumption 280 gram per kilowatt hour. The volumetric ratio 1 to 9.5, and the reference condition for those performances is entry air at 20 centigrade and atmospheric pressure, let's say 100 kilopascal. In the video comment and also here in the presentation, we leave also the reference of the given motor data. In the first model, we consider ideal gas and isentropic transformation. The air parameters have been already calculated in the slide number 5 of the previous presentation. The pressure at the state 1 is also 100 kilopascal. The temperature, as already said, 20 degrees. We call R the volumetric ratio, which is the ratio between the specific volumes of the state 1 and 2, and it is also the ratio of the volumes capital V1 over capital V2. knowing the displacement and divided by 4 because the cylinders are 4, we can express the difference of the volumes of the state 1 and 2, and also we have two equations in two unknowns, and we can solve them, finding for the volume of the state 2 70 cubic centimeter and for the volume of state 1 667 cubic centimeter. By means of the state equation, we calculate the mass inside of the cylinder, which is 0.793 grams, and with the definition of the specific volume, we calculate V1 as capital V1 divided by the mass and V2 as capital V2 divided by the mass. We get 841.1 and 88.3 liter per kilogram respectively. The pressure at state 2 we calculate by using the equation of the isentropic transformation. Therefore, P2 is P1 into the volumetric ratio to the power K and turns into 2338 kilopascal. Assuming the temperature at state 3, the maximum temperature, being 2300 Celsius, we can calculate the pressure of the same state by using the state equation, and we land to 8365 kilopascal. The pressure of the state 4 we calculate in the same way as the pressure of the state 2 by means of the isentropic equation, and we find 358.8 kilopascal. In the chart is represented the cycle in the diagram PV using the tool Thermonator. Below a table with the thermodynamic states. In the two red frames, the input values. The pressure values of the states 2 and 4 are slightly different from the calculated values in the slide 18 because of rounding errors of the volumetric ratio. We consider here a control mass and therefore we use the thermodynamic work. From the equation number 2, we remember first thermodynamic principle, delta U equals Q minus L. The transformations 2, 3 and 4, 1 are isochoric. Therefore, the thermodynamic work is 0. The Q of the transformation 2, 3 is capital U3 minus capital U2. That is capital M into CV into T3 minus T2, 1052.2 Joule. In the same way, we calculate the Q of the transformation for 1, and we obtain negative 426.8 Joule. The thermodynamic work of the cycle is the sum of the works of all the transformations, or we can calculate as the sum of the heats of all the transformations. But since two transformations are adiabatic, they remain only the calculated heats above. We get 625.4 Joule. What is the power of the cycle? We remember that one cycle corresponds to 2 revolutions of the motor shaft. The power is 4 times the thermodynamic work divided by delta T, 4 times because we have 4 cylinders, and we add also the mechanical efficiency because we want the mechanical power. Delta T is 2 times the frequency because of 2 revolutions, also 2 times 60 divide RPM. RPM is 5400. We obtain 0.0222 seconds. If we replace the numbers, considering a mechanical efficiency of 80%, we find a mechanical power of 90 kW, which is different from the power of the datasheet, that is 114 kW. And what is the efficiency of the cycle? The thermodynamic efficiency is the thermodynamic work divided by the input heat, and therefore 59.4%. What is the thermodynamic efficiency we would expect if the volumetric efficiency were 90%? From the datasheet, we have 280 grams of gasoline needed to produce 1 kilowatt-hour of mechanical power. And considering that the heat net value of the gasoline is 11.6 kilowatt-hour per kilogram, we can express the efficiency in this form: 1 divided by 0.28 kilogram divided by 11.6 kilowatt-hour per kilogram, and we obtain 30.8%. But this is the total efficiency, also the product of the thermodynamic, the volumetric, and the mechanical efficiency. From that relationship, we can solve for eta T, and we find eta T equals 0.308 divided by the product of the remaining efficiencies, and we land to 43%, which is significantly less than the calculated efficiency above. That means our model is not matching very well. What to change? We adopt now the second model, a perfect gas, and changes the two adiabatic transformations into irreversible ones. For that, we introduce the adiabatic efficiencies of the compression and expansion transformations after finding the new isentropic temperatures T2' and T4'. For finding them, we use the application Thermonator. The efficiency of the compression is, for definition, T2' minus T1 over T2 minus T1. And we say this assumes the value of 90%. Replacing the corresponding temperatures, we find for T2 the value of 472 degrees. The efficiency of the expansion transformation is, for definition, T3 minus T4 divided by T3 minus T4', and this assumes the value of 93% is our choice. Replacing the corresponding temperatures, we find T4 being 1118 degrees. We calculate now the work, and this assumes the value of 628.5 joule. The power does not change much versus the one calculated in the ideal case, but the efficiency is now much closer, 46.9%. Also, this is a better result, even not perfect. We remember that the theoretical calculation for the isentropic transformation says T2' equals T1 into R, the volumetric ratio, to the power K minus 1, and T4' equals T3 into R to the power 1 minus K. But we did not use this formula because K for the perfect gas is not constant. Therefore, we rely on the Thermonator tool. What changes if we modify the volumetric ratio, increasing from 9.5 to 12? The answer is the volumes change, and also the mass. The volume capital V1 and capital V2 will assume the values displayed, and also the mass will be 0.769 gram. Correspondingly, also the specific volumes V1 and V2 will change. If we keep the same temperatures of the state 1, of the state 3, and the same efficiencies for the compression and for the expansion transformations, Then we find for the work the value 631.1. The power still stays at a very similar value, 91 kilowatt, but the efficiency will increase dramatically up to nearly 51%. Also, it means that we need less fuel to do the same work. Why we don't do it? Normally, in the combustion motors working with the Otto cycle, we do not use these high values of volumetric ratio because the temperature T2 increases too much. In this case assumes the value of 566 degrees, and that causes premature ignition, also detonation. Nevertheless, we do this job for the diesel engines instead. We will see this in the next slides. Some observations. We observe there are deviations between the theoretical and the real data. In particular, the power is 20% less than the datasheet value and the efficiency between 3 and 4% greater. What can be the reasons behind? First of all, the substance is changing after the combustion. From the air are produced combustion gases that increase the heat value at constant pressure, and this can justify an increase of the real work. Moreover, the cycle cannot be simplified as we have done, because we have to consider also the intake and exhaust phase that produce a negative work as a consequence of the pressure drop. We start now with the diesel cycle. What is the difference between the diesel cycle and the Otto cycle? We can see in the PV and the TS charts here on the right side the representation of the cycle in the ideal case. First, the fuel is different from gasoline. The starting condition 1 is achieved by a turbocharger, and the pressure is generally greater than the atmospheric pressure. The transformation 2-3 is isobaric. The fuel injection starts after the piston reaches its top end and there is no spork. The transformation 4-1 is just theoretical because the expansion continues throughout the turbine. The work of the turbine is taken from the outlet gases and it is free of charge, so we do not count it in the overall cycle. We'll see a schematic in the next slide. The volumetric ratio R is much higher, in the range of 20, and the revolution speed RPM is typically lower, in the range of 3500. Also, in this case, to make it more interesting, we refer to a real motor. We take the Toyota QL-TE, which has a displacement of 2446 cubic centimeter, very similar to the one we have seen with the Nissan motor for the Otto cycle, and then also 4 cylinders. The power output is in this case less, 71 kilowatt, and this takes place for a revolution speed of 3800. The specific consumption is 200 gram per kilowatt hour, which is definitely lower than the one seen for the Otto cycle, and the volumetric ratio is 1:21. The entry air conditions after the turbocharger are 60 degrees and 200 kilopascal. Here we can find the reference to the motor, which is also available in the video comments. As the first model, we take a perfect gas and isentropic conditions. The pressure at state 1 is 200 kilopascal, the temperature 60 degrees, the volumetric ratio 21, and with the same formulas seen for the Otto cycle, we can determine the volumes of the states 1 and 2, and we find 642.1 and 30.6 cubic centimeters respectively. From the state equation we find the mass working in the cycle, 1.343 grams, much higher of the mass already seen for the Otto cycle, and this because of the turbocharger. With the same formulas we can also calculate the specific volumes of the states 1 and 2, which are definitely lower, much lower, almost the half of the ones already seen, and the pressure of the state 2 is the pressure of the state 1 into the volumetric ratio to the power K. We find 14,195 kilopascal. The transformation 2-3 is isobaric. We assume a maximum temperature of 1800 degrees. The transformation 2-3 is the product of the mass, the specific heat at constant pressure, and the difference of the temperature. We find the value here displayed. The work of the same transformation is the product of the mass, the pressure, and the difference of the specific volumes, while the heat of the transformation for 1 is the difference of the internal energies, also the product of the mass, the specific heat at constant volume, and the difference of the temperatures. The work of the cycle is the sum of the heats of the transformations 2, 3 and 4, 1, because the remaining ones are adiabatic. The power of the cycle, considering also that one cycle is 2 revolutions, we can get from the same formula already used for the Otto cycle. 4 times thermodynamic work divided by delta T into the mechanical efficiency. The delta T is 2 times the frequency and is 0.0316 seconds. Replacing the value and considering the same mechanical efficiency as the motor seen before, we find a power of 101 kilowatt. The efficiency of the cycle is the thermodynamic work divided by the given heat, also 60%. The thermodynamic efficiency we would expect instead, considering a volumetric efficiency of 1 because we have the turbocharger. From the datasheet we know that 200 grams of fuel corresponds to 1 kilowatt hour, and since the heat net value of the diesel fuel is 11.9 kilowatt hour per kilogram, we can determine the overall efficiency of the motor, which is 42%. Therefore, the thermodynamic efficiency is the overall efficiency divided by the mechanical efficiency, only because the volumetric is 1. We find 52.5%. See the presentation of the same cycle in the diagram TS and also the calculated parameters and processes. For the meaning of perfect gas, please see the slide number 16. In the second model, we stay with the perfect gas, but we change the 2 adiabatic transformations into irreversible ones. And we introduce the adiabatic efficiencies, same as per the Otto cycle, for the compression and expansion phase. First, we calculate the isentropic temperatures T2' and T4', that are the temperatures considering the isentropic case. The definition of the adiabatic efficiency is the same as we have seen before. For the compression phase is T2' minus T1 over T2 minus T1, and we keep the same value of the cycle already seen, 90%, and replacing the values we find for the temperature T2, 838.7 degrees. The adiabatic efficiency of the expansion transformation is T3 minus T4 divided T3 minus T4', and still we keep the value already seen of 93%. Replacing the values, we find T4 771.4 degrees. The work is the sum of the heats over the transformations 2, 3 and 4, 1 and is 816.8 Joule, as we can get from the Thermonator table below. The power in this case is closer to 71 kilowatt, even not perfect, while the efficiency, the thermodynamic efficiency, is much better, almost same as the one expected, 52.1%. The theoretical calculation for the isentropic transformations, we have used the Thermonator application, but we could have used the formula 37. The problem is that K is not constant and therefore this calculation is not accurate. As we have seen for the Otto cycle, there is of course some approximations which cannot be neglected, but for the sake of our scope, this is satisfactory. See you in the next presentation. Thank you for your attendance. Bye bye.